Okay, this is 8.3. This is on exponentiation ciphers. So this section sort of forms a halfway point between basic shift ciphers and affine ciphers and full-on RSA encryption, public key cryptography, etc. So by way of intro, just a reminder, in 8.1 we looked at two things. Looked at shift ciphers. These were the case where we had the ciphertext, took the plain text and we added some B, reduced it, mod 26, and here, let me pull up these, this was with, technically speaking, B could be anything. Realistically, because we're mod 26, the values, the only values that make sense are those between 0, including 0 and 25, although 0 doesn't really make much sense either because we're not really changing anything. But you could do it. And then we did affine ciphers. What we did C was A, P plus B, mod 26. This was with, again, B could be any of these. And technically A could be any of these. This was with A had to be co-prime to 26, or else it wouldn't be invertible. So the thing to point out here is that really any function that's invertible could work. All right, let's say any assignment. Which would be like, for example, C is congruent to some function of P. On 26 would work. So what we'd like to do is sort of explore another one, but we're actually going to do slightly different than that. You'll see why. Let's say another with a variation. That variation will become clear as we proceed. So the first thing we want to do is I want to modify the letter slightly. In other words, the assignment of numbers to letters, or letters to numbers. So what we'll do is we will we'll assign A to be 0, 0, so, and B to be 0, 1. So I'm putting a leading 0 in all the places where it's needed. So like when we get to Y, Y will just be 24, and Z will be 25. So we're padding them to 2 digits. So the reason for this is so we can string multiple letters together in groups. Like basically this is so we can group letters. So for example, we're going to do JU. Right, so J is 9 and U is 20. Right, so this is the J, this is the U. And the reason for padding would be because otherwise something like 1, 1, 1 could mean say 1 and then 11, or it could mean 11 and then 1. Right? By having the zeros, let's say by having the padding, 111 would come across as 0, 1, 1, 1, and 11, 1 would come across as 1, 1, 0, 1. So really the 0 is just there as a sort of a placeholder to make it a, like in this case, a 4-digit number. Or if you wanted to do 3 letters, you would have a 6-digit number, and so on. So we'll do that, and we'll continue that as we go through the rest of the encryption methods. And the other thing to remember for today, which is sort of out of left field, Fermat's little theorem. So just a reminder of what that said. That said if P is prime, and A is an integer with P not dividing A, and A to the P minus 1 is congruent to 1 mod P. So here's where we're going to have a prime P that comes up, as well as a plain text capital P. So try and find some way of making those distinct for yourself. So what we're going to do with these is we're going to move on to exponentiation ciphers. So let me, this is all prep. So let me clear the screen. Just the things to keep in mind as we go forward is the Fermat's little theorem. Sort of put that in your head. I won't leave it up because we'll probably need to erase it anyway to fill up the screen. And then this deal with padding. I think it's the 2 digits. If you can remember these, then we're good moving forward. So 2 exponentiation ciphers. So we'll do this in a few steps. This is a little more complicated than what we did before, and that's okay. So the first thing we'll do, so we'll talk about encryption, then we'll talk about, we won't say anything necessarily about, like there'll be some details about Fermat's little theorem that we'll ignore for now, and then when we get to decryption, we'll sort of figure all that out, right? So for encryption, we just want to talk through the process. So the first thing we'll do is we're going to say let P be an odd prime, and let E be a positive integer that has GCD of E and P minus 1 equal to 1. So what we'll do is we'll take, and generally P will be pretty big, not like 7, it'll be much larger. We'll see an example in a second. So we take the plain text and we'll divide it up, or let's say this way, we'll group the letters, is the way that I wrote it in the notes. And the way we'll do this is as follows. I'm going to group it so that the value of no group could possibly be greater than or equal to P. So for example, this is the one I'll use. If we set our prime to be 3001, this is prime. I checked. Then what I need to do is I need to divide my plain text into no more than 2 character chunks, right? So then what we would say is we'd say use, let's say, groups or blocks, if you like, of 2 characters, because for 2 characters the biggest number you could get would correspond to ZZ, which would be 2525. This corresponds to ZZ, right? And I want to ensure that 25 in this case is less than 3001. I don't want to spill over that, right? You know, on the other hand, if we did say R prime to be 377173, that's also prime, you can check. Then we could use 3. We could use blocks of length of 3 characters. This would be because 252525 is less than that number. So you never want to sort of have it too big, and the reason is that the numbers might spill over if I'm taking things mod 377173. So now when we divide it up, if we divide it up into 3 character blocks, that may not match the text, right? The text may have like 11 characters and 3 character block spills over. So we pad if necessary. So pad the plain text to make it a multiple of the block size. And you can pad it with anything. It doesn't really matter because when we decipher it, you'll sort of see what the padding is, but using a capital X is sort of traditional in textbooks. So then for encryption, we do the following. So what we're going to do is we're going to go to sort of standard nomenclature for cryptography. We're going to say that Alice is sending a message to Bob. These are sort of fairly traditional names for our cryptography. So Alice will use the encryption key. So the encryption key, let's say, which consists of the pair EP. So remember, go back to the beginning, just check it out on the left hand side, that P is an odd prime and E is positive integer with the GCD of E and P-1 being 1. And for now, don't worry about why that requirement's there. Not at all clear, but this is what Alice needs to know. She has these 2 pieces of information. So for each plain text block, could be 2 characters, could be whatever. This is what she does. She figures out the ciphertext. The ciphertext will be P to the E. This is P to the E mod on little p, right? Now, this little note here, because we're mod little p, and little p may be like in our first example, little p is 3001. It's entirely possible that C is bigger than 2525. So we're not going to convert it back to letters because it's possible. So we're taking the least non-negative residue mod little p, but that might be too big to convert to characters. So now I'll just say specifically, and we'll see an example, that C cannot be rewritten as letters. We don't. So we simply don't. We send the numbers. Because sending letters doesn't matter anyway. Sending the numbers is absolutely fine. So let's do a simple example, which will fit in right here. So we'll do actually, it's probably not going to fit in right here, but that's all right. So this is, we'll do the following. Alice will use EP, which will be 479-3001. So an observation here, you can check this if you like, is that in this case, the GCD of 479 and 3000, that's P-1, is 1. All right, so you can check that that's the case. So she wants to encrypt the word love note. The first thing that she does is she divides this up into 2 character chunks because her prime 3001 is big enough that 2525 would fit. So she'll divide it up into 2s. Right, so let me do that on the left. So here's the process. She divides it into 2 character blocks. So for each of these, called P, so P will be a 2 character block as numbers. She does exactly what we just said. She does C is congruent to the plain text block to the E479 mod 3001. So this is this deal about like fast exponentiation we talked about earlier in the course, that we have to be able to do this pretty quick. But since you're modding 3001, you don't actually have to raise the number to the 479th power first. You can raise it and reduce and raise it and reduce. So this is pretty quick on a computer doing this. This is not a difficult procedure. So for each, she does these, right? So here's the result. I'll write this all down. So she takes LO, that's 1114. So again, the L is 11, the O is 14. Takes VE, which is 2104. So that's a little illegible. Takes NO, that's 1314. Takes TE, that's 1904. And then she takes each of these, raises it to the 479. And she does this all mod 3001. And the result is 0169, 0317. I'm padding these out with zeros too because we need to make sure that when we send it, we send the zeros that are sort of jammed in the middle. And 1697. So this guy, this is considered the ciphertext. This is sent to Bob. So, question then becomes, what does Bob do? So how does he decrypt? We'll put this under B, decryption. So, this is what's going on. So this is reversible, and this is why. So the fact that, remember what our guarantee was with the GCD of E and P minus 1 is 1. This guarantees that E has a multiplicative inverse mod P minus 1. In other words, it guarantees that there exists a D such that DE is congruent to 1 mod P minus 1. Now this can be found using the Euclidean algorithm. We'll do an example in a little bit. So then what happens is for a ciphertext block, C, Bob does the following. So the thing to keep in mind is, this is a parenthetical, keep in mind that Bob has C. He knows that C is P to the E mod P, and wants P. Because Alice did the P to the E and got the C. And so Bob doesn't know P to begin with, he just knows C. He wants to get P back. Right? But here's the deal. Take a look. So he takes the ciphertext. He does C to the D. Right? He does that mod P. So why? So here's the deal. When he does C to the D, right, this is the same as P to the E to the D. Now he doesn't know P, this is just the mathematics, right? That C is P to the E. Right? Now, this is the same as P to the ED. But PD, if we, or rather ED or DE, if you like, it doesn't matter which way around we have it. If you look on the left, right there, we know that DE is 1 mod P minus 1. So DE is 1 plus a multiple of P minus 1. So this is P to the 1 plus a multiple of P minus 1. This is all mod P. I'm going to write that at the end. Actually, we'll do that as we go. Be responsible. Now, this is the same as P to the 1 times P to the P minus 1 all to the K. That's just rearranging the exponents, nothing special there. But here's the kicker, is that this thing in the parentheses, right, this is congruent to 1 mod P by Fermat's little theorem. And we know there's a requirement for Fermat's little theorem. So the requirement here is that little p does not divide big P. This is because big P is less than little p, and you can't divide something that's bigger than you, or you can't divide something if it's smaller than you, rather. So what happens in this case is Fermat's little theorem says like, oh, this just reduces to big P to the 1 to the K mod P, and this is just P. So what that does is that allows him to get the result back. So he then knows P. So let's do an example. So again, just before the example, just so we're clear on the fact, note here is that to send it, Alice needs EP with GCD E and P minus 1 equal to 1 to send. Well, really, let's be clear, to encrypt. And Bob needs D, comma P. He needs both of these with ED is congruent to 1 mod P minus 1 to decrypt. And the existence of that D is guaranteed by the GCD fact. Right? So here's an example. So let's suppose, actually before we say he receives it, let's say, I'll tell you what the D is for this particular, for Alice's. So Bob knows, and he figured this out, they figured it out together because they shared the information, doesn't really matter right now. We'll talk more about that as we go. So Bob knows 119.3001 corresponding to that 479 3001. So again, the connection here is that between all these, this is not going to be obvious, just so that you know, is that 479 times 119 is congruent to 1 on 3000. Let's suppose he receives the encryption, the ciphertext, which would be 2672.0317, and he has to know the block size. By the way, you know, maybe he knows that Eve always sends in things in blocks of 2. 1665 to 110 0246 1749. This is fairly lengthy. 0017 and 2112. So this is what he does. He does to the 119 mod 3001 for each. And we'll just say, and he gets, so I'll just tell you what the output is. He gets 1800, and he gets 2104. Sorry, that's badly written. 2104. And he gets 2414. And he gets 2017. Now these things should correspond to strings of letters. So if you ever do this and you get like 26 as one of those, then you made a mistake. It's 1105. And he gets 1314. And he gets 2223. And that corresponds. 1800 is SA. 2104 is VE. 2414 is YO. 2017 is UR. 1804 is SE. 1105 is LF. 1340 is NO. And then WX. So clearly this is save yourself now. And again, it's pretty clear that the X is padding that Alice had to use in order to sort of round this out to 2 characters. So that's how the decryption works, right? So what we want to look at last is like, okay, how do you break this? And I don't mean it with like frequency recognition. I mean, for example, if Alice has an E and a P, and Eve, who's eavesdropping, she finds the E comma P. Like, how does she construct the D, right? So we talked about this briefly, but let me work through a specific example of how she can do it. And then we'll sort of see what the weakness is here and like what that means computationally. So let me clear this off, and then we'll just do this last part on breaking these ciphers. So 3. Breaking exponentiation cipher. It'll be good to keep this in mind, because when we move to public key cryptography and RSA algorithm, it's this jump in computational difficulty that is critical in figuring out the decryption. So let's say, suppose Alice uses E and P. So Eve, let's say, finds this out. And she wants to know. So don't worry right now about how she finds it out. Somehow. And she wants DP because she wants to encrypt Alice's secret communications that she's sending to Bob, for example. Right? So in this case, since Eve knows P, she knows P minus 1, presumably. She can subtract 1. So then she can find D via the Euclidean algorithm. Now, if you've forgotten how this works, let's make it clear. This is because she can find alpha and beta in the integers with alpha E plus beta P minus 1, not congruent, let's be careful, equal to 1. Right? So again, this is because, remember how this works, if the GCD, so this EP, this has the property that the GCD of E and P minus 1 is 1. So the GCD can be written as a linear combination. That's what we did right here. This is a linear combination of E and P minus 1. So she finds this out, she does her Euclidean algorithm. That's computationally difficult-ish. I mean, it's not difficult, right, for a computer, but it's difficult for a human if there's a lot of calculation. So we can see, for example, it's you know, it's harder than other calculations, it's harder than simple calculations. So she just takes this, she reduces the whole thing mod P minus 1. The P minus 1 bit vanishes. and then she just lets the alpha be the D. Right there, mod P minus 1. In other words, this will be D, if you like. So, then she knows D, and then she can decrypt. So, for example, suppose that Alice uses, let's do a different one. EP is 6893343. So then she knows, right? So E finds this out. So she knows, because she knows this is what Alice does, she knows that the GCD of 6893342 P minus 1 is 1. Okay? So she uses the Euclidean algorithm. And she finds out that, or she, let's say, solves. Let's show the intermediate step. 689 alpha plus 3342 beta equals 1. Right? When she does this, she gets 689 times 941 plus 3342 times negative 194. That's what she gets, Euclidean algorithm. She reduces mod 3342. So she gets 689941 is congruent to 1 mod 3342. And so that is the D. This is the D corresponding to Alice's E comma P, and then she can decrypt. So just a sort of a closing note, right? So she can decrypt basically anything that Alice sends. So as a closing note then, you know, if this is just Alice and Bob, right? If Alice is sending things to Bob and that's it, and maybe Bob is sending them back, they can just share these, and, you know, like Eve doesn't even need to know E comma P, right? If it's just Alice and Bob, then Eve might never know E comma P, and then it's no big deal, right? But the point is, like the big point, which will change shortly in the next section, the point is that knowing how to encrypt leads you to knowing how to decrypt. Right, so knowing EP makes it easy, Euclidean algorithm easy in this case, to find DP. So the looming question is it possible to know EP but have it difficult to find DP? So could it be possible to know EP but hard, where hard means like millions of years, to find DP? Because then, for example, Alice could just tell everybody, like, well, here's EP, that's it, and nobody could decrypt except for Bob, who she told DP to, right? So like the deal is in this case, so then, you know, Alice, like EP could be public. Right? Not in this situation, but in an ideal situation, you know, this could then be public, right, and only Bob knows DP. Right, nobody else can find it out without a lot of work. Right, because because it's hard work. So this is what we'll look at next, and that's related to public key cryptography.